Now a diffusion current happen if the electron concentration on one side of the semiconductor is greater than the electron concentration on other side of the, not the semiconductor, of a metallic plate or metallic rod. Then these electron will move from higher concentration to lower concentration, and there is a movement of electrons, so there is a diffusion current. Now here we have more holes, okay, and here we have more electrons. So what it means that there will be a diffusion current. Electron will move from N region to P region, and holes will move from P region to N region, even in the absence of external electric force, because there is a concentration gradient. Concentration of hole is higher here and zero here. There are few holes, minority carrier, charge carrier, but we ignore that charge carrier. And similarly, electron concentration is higher here and lower and zero here, so electron will move to this side. So it means that hole will move to this side, okay, and electron will move to P side. Suppose this part diffuse, like electron from this part move to this side and hole from this region move to this region, then what will happen? I will plot this figure again. Suppose we have, this is the junction, okay, electron, holes here, but here we have holes also, but that holes diffuse to the N region. So holes diffuse to the N region, what it means? It means that there is a fuzz negative ions left, negative ion left on this side. An electron diffuse from N type to P region to P region, like from here to here. So here we have positive ions. And we have electrons here. So these positive and negative ions are in a region which is very close to the junction. Why there are positive ions? Because we have donor atoms, arsenic, which is 5 outermost electrons, okay. Among these 5, 4 participate in the bonding process. 1 electron is free. If that electron is given to the conduction band, then this arsenic atom acquire a positive charge. So the electrons now gone from this region. So here we have the ionized arsenic atom left. Similarly, here we have boron, which is 3 electrons, okay, and these 3 electrons are participating in the bonding process. It acquire another electron or accept another electron. So once it accept electrons, so it's have a negative charge. If the holes move from there, if there is a hole here, then these hole and negative charge balance each other. But if holes move if you remove the holes, then we have a net negative charge, which is this one. Now again, we have still concentration gradient, so it means that these electrons also diffuse across the junction, and these holes also diffuse across the junction. So we have the depletion region, we have now 2 layers of positive ions here, because the second layer also diffuse, and we have 2 layers of negative ions here, because the second layer also diffuse, and we have holes here. And we have electrons here. Now what happened after this? Do these electrons also diffuse, or do these holes also diffuse across the junction? The answer is no, because we have a lot of negative charge here and we have a lot of positive charge here. If these holes tries to diffuse across the junction, then this positive layer, positive charge region push this electron, because they both are positive charge now, so they push these holes backward. Similarly, we have a negative charge and these electrons have a negative charge. If this electron tries to diffuse across this junction, then this layer of negative ions will push this electron backward. So here we have a stage is reached in which the diffusion stop. Diffusion of charge carrier stop, and the junction become at equilibrium. Junction is at equilibrium, and the junction comes to is at equilibrium. Okay, so there is no further diffusion of charge after a certain amount of diffusion of charge. Now there is no diffusion, the junction is at equilibrium. So on one side we have positive charge, on the other side we have positive ion, and on the other side we have negative ion, and we have a region which is, this region is called depletion region. This positive and negative charge region, this region up to this point is called depletion region. Now there is a positive charge, there is a negative charge, so it means that there is an internal electric field developed here, which is let me check. Which I represent by this xi, and because of this electric field there is a potential developed. So the potential will be, there is a potential developed across this junction. This side become positive, this side become negative, so that potential is called barrier potential. This potential is called barrier potential. This is all about p-n junction. Now what happened? Just let me check. Okay, now I will draw these two figures again. Okay, we have negative charge here, electrons, and we have holes here. This is the time when the junction is just developed. We prepare this p-n junction. Then we have conduction band, okay, which is EC, and we have valence band, which is EV. This is P, this is N, so this is for P. We have Fermi energy here, EF, okay, and the intrinsic Fermi energy is in the middle of EC and EV, which is EI. Now we have p-type. Here we have EV, here we have EC. In p-type the Fermi energy is close to the conduction band, so here we have EF, and the Fermi energy is at the middle of EC and EV, intrinsic Fermi energy. Now once electrons move from N region to P region and holes move from P region to N region, we have this situation. Okay, I will make a bigger figure. Here we have positive ions, okay, here we have negative ions, and here we have holes, here we have electrons. Now there is an external electric field. Its direction is from this positive to negative, and we have a potential difference developed here which is called barrier potential VB. Now the junction is in equilibrium. There is no diffusion of electron and hole across the junction. Now what will be the band structure? Sorry, the band structure look like this. Sorry. Now the band structure of this PN junction after equilibrium looks like this. So we have a situation which I will plot. Now the Fermi energy of these two levels, like the EF of P-type and EF of N-type, will come to the same place. This is EF. Here we have EC, EV. Here we have EC, EV, and this is the Fermi energy. Now the intrinsic Fermi energy is at the middle. Here the intrinsic Fermi energy is at the middle. So we have a potential difference. This is the potential difference, okay. A barrier potential. So here we have more electrons in the conduction band and less holes in the valence band. Here we have more holes in the valence band and less electrons in the conduction band. This represent this part. So holes are in valence band, and this represent this part, which is electron in the conduction band. While this depletion region, there are no holes and no electrons, but there is a potential barrier potential, which is this one. Now if electrons move from this N region to P region, then it needs to overcome this barrier potential. So it needs an extra energy so that they will jump from here to here. So it needs this barrier potential, this much energy to move this electron from here to here. Similarly, if a holes move from this region to this region, then it needs this barrier potential. It needs to overcome this barrier potential. Means if the barrier potential is, let's suppose, 5 volt, then it's need 5 joule. Yeah, it's a potential, so it's joule. Then this hole needs 5 joule energy to overcome this barrier potential, or to go from here to here. So this is all about PN junction. In the next video, we will discuss forward bias and reverse bias PN junction. Thank you. Hope you people understand it. Thank you.